Friends, today's presentation is very important as we are doing a lot of development work in hilly areas, and we all know as a part of widening in hill areas, we are doing a lot of cutting works on hillside. And when we do the cutting, it destabilizes the hill slopes. And last year we have already witnessed what had happened in Himachal Pradesh and other hilly areas. And for this purpose, we have to be very careful in geotechnical and geological investigation, and also from environmental and social point of view. The slope stabilization, hill slope stabilization is a very wide subject, but today we are focusing on cut slope stabilization. And in today's presentation, we would cover the issues involved when hill slope is cut, generic measures to be taken for its stabilization, and technical approaches for its proper engineering. We are lucky to have with us Mr. Ashish Gharpure, who is presently managing director of Genstu Construction Limited. He has very wide experience and he's very knowledgeable. And now I request Mr. Ashish Gharpure to, if Chairman Saab has to add something, and after that we can proceed with the presentation.
So, my friends, everybody present over in today's capacity building session. This is seventh in chapter of the series which we started. I'm getting lots of feedback from concessionaires, from team leaders, from IPDs that it is this capacity building session is really useful. Dr. Ashish, I'm very grateful to you. I'm seeing what about I was listening about you from Alok. Alok, we are we are lucky to have him. Such a wide experience he has. So now over to Dr. Ashish. Thank you. All the best.
Sure, sir. Yeah, thank you very much, Chairman sir, for setting that tone and giving the background of it. I'm very grateful that you have given this opportunity, and thank you, member sir, also for that nice introduction. So I'll straight away go with this presentation. I'll just stop my video so we don't interfere with the presentation. Right. So, as members have currently, correctly pointed out that it's a very wide subject. We are trying to focus it on a limited cut slope stabilization part of it, and we'll go through, the details of it in step-by-step content manner. So basically, slope stabilization, what kind of issues we are facing, mostly from highway perspective. Then what kind of generic measures available? These are like a menu card presented, and we have to pick and choose what we want for our specific need. So there are various types of materials available, and we'll have to treat maybe one as soil stabilization, one as a rock stabilization, and deal with it. Then we will touch upon the approach to evolve solutions. And this is very important because just going, looking, seeing the things and giving some solution is one thing, and definitely experts can do that. However, going into the details, turning qualitative into quantitative to the extent possible, and then analyzing and detailing it would give much more value to the solutions obtained. And then I'll just give glimpses of some case studies, and if needed, we can get to question and answer session. So we do face these kind of things. We are aware of it, but just a glimpse of it. This is Kedarnath. So right hand side, you can see. So we were talking about debris flow, then hill cut slope, and there are some very vast and big slope cutting. The left bottom is actually from Tupul, Manipur, where a huge landslide happened. 43 lives, gone with that. And we also face from valley side slides also, because the hill slope is continuing on either side. Then particularly when you have a river flowing downstream, then you also see lots of valley side cutting and slipping off. Next, please. Then we also deal with rock cut slopes. Now, some rocks can be very stable, and you don't even you can cut vertical and it will be stable. However, we need to monitor each rock type and its bedding planes, joints, and detail to know what kind of failure is possible. So there are favorable and unfavorable conditions of rock cut and slopes. So we'll deal with it as we go next. But and there are conglomerate material as right top corner screen you can see. So type of failures, landslide definition is very basic, that any downward movement of soil and rock, and it will be a landslide. In cut slope, it is predominant because you have taken off the support system of it. There could be flows when topsoil flows on top of rock surfaces, and very common cause. And you can see that practically everywhere that topsoil will slide down over a rock surface, as mentioned in flow here on the left hand side. Then there are toppling of rock, overall slump, classic slip failure, as well as slide of one rock layer on top of other rock strata underneath. Then there are creep, very gradual movement, where mostly this is clay soil, conglomerate type of material, where you can see everything tilting and moving very gradually. It may not come down in one go, but it may keep on increasing till a point where you can see the failure. And there are topplings and overhangs failing and so on. What happens is it's all due to alteration in topography, increased pore water pressure, or very steep gradients, sudden increase in overburden or other loads. And of course, we know that most of it would happen during a rainfall, right? Then sudden deforestation could also be one cause for this. Next. Now, failure can occur within the slope surface, so we call it slope failure, or the slip may occur right at the toe, where the horizontal portion is not affected, but the slip is coming right up to the toe, so it's a toe failure. Or otherwise, there could be very deep-seated failure, leading to not only sliding, but also on heaving side, on the horizontal side of it. So we'll have to analyze which type of failure it is and then deal with it with different solutions. Next, please. Then comes to this, once we are dealing with soil, these kind of failures, the slip circle failure. But when it comes to rock, the failures are defined mostly how the rock, the structural geology of a rock is, and the orientation and how steep the slopes are. So there could be a free fall from a vertical cut to rolling down of stones and sliding of rock over the other rock surfaces. Uh, More or less causes are same: gravity, climatic variation. So due to heat variation, also temperature variation of surface and inside of a rock mass, there could be layers getting created, weathered layers, and then it slips. Then of course, if the slopes are steep, loss of shearing strength, if the rock is very highly fractured mass, water is always a cause, whether it's rock or soil, frost, heave, earthquakes, other vibrations, all of these can cause failures. Next, please. Now, one thing people ignore is erosion, that it's not taken as a serious failure or anything. People are aware about landslides or landmass slipping, soil landmass. People are aware of boulder coming down or rock mass coming down. Erosion is a phenomena, superficial phenomena, but it can actually get to a very difficult stage depending on surface erosion, but second, also subsurface erosion. If a continuous water flow is there. Please, next slide. So this is just to show how grave an injury and erosion can cause. So this is a project site we had in North Sumatra Island, Indonesia, where you can see the gullies getting formed, and not only that, bottom right, if you say, big sinkholes are getting created because of subsurface flow. Even an elephant can go into that. And this all happened within a day when I was there, when the cut was open and heavy downpour happened, and then these kind of failures started. Next, please. So erosion has to be taken seriously as well. Now, what kind of solutions we come across, and mostly, most of it is known. I'm just trying to put some highlights. One simplest solution is the slope is failing because it's steep. So what do? We cut and make a moderate slope so that it can survive. So removing the material from area, driving the slide, adding material to the area, maintaining stability, that is putting a weight on the toe side, and reducing in general the slope angle. I must caution here that this generic solution may not work with some types of soils and rock, right? Particularly, I'm talking about shales, but even other where swelling or the slake durability comes in picture. Next, please. There is a request coming that that stop sharing ribbon can be eliminated. If I can request the presenter. So in any case, this is the cut profile. So how you moderate the slope, right? Next, please. Can that ribbon be taken off, sir? Once again, requesting that there is a ribbon coming that stop sharing and hide. I don't know how. Yeah, thank you very much. Now, coming to the most important part of it, of any slope stabilization, which is drainage control measure. It's so important that I don't mind repeating it several times in this presentation, that if there are something has to be highlighted about any slope stabilization, it is drainage. It is so important. I would put 80% weightage on drainage control. So 80% of solutions may come from drainage control alone, whereas the cost of drainage control may be only 20% of overall cost, and the vice versa, that 20% solution may come from 80% of the cost of rest all solutions. So can't emphasize enough about drainage control measures. There are various types of drains and structures that can be created to take off the water from the matrix of soil and rock, and thus making it safer. So there could be surface drain, trenches, counterfort drains, vertical wells, well point system people are aware of, where you can pump out the water, drainage tunnels, galleries, vacuum dewatering. Several measures are there. Including plantation, because as you know that plants transpire the water from ground to the air. So even that could be a very good solution for drainage control alone. Forget about the benefit of erosion control. Next, please. So here I'm just showing that how elaborate a drainage can be done in a particular hilly environment, because it's not very easy. So you have to actually access the water and then take it out. So drain pipes, subsurface drain, French drains, connecting them to surface drains, lots of things that can be done for drainage systems. Next, please. And wherever the failures has occurred, you still need to see that how do we attain a drainage mechanism. I keep telling some of our freshers that we have to think like a droplet of water, which is coming down from air, and then it is flowing. Some part of it is going as surface flow, some as subsurface flow, but all of it eventually should go and merge with the local stream. And what best we can do to make sure that it happens. So one more figure is there, just to tap may show that. So we have to make an arrangement of catchwater drains or cutoff drain. Then in the berms of this slope, you can have some berm drains. All this must be connected to a cascade kind of drain which takes it down, and then you can merge it eventually at toe drain or roadside drain, and then through culvert it goes into the valley or merges the stream. So a very elaborate arrangement of drainage is needed, and that helps in slope stabilization as well. Next, please. So the various types of drains, whether it's gabions or drain pipes, cascade drains, V drains, is just again pictures of all kind of drain arrangements and how it is done. Next, please. So these are gabion cascades and how they are constructed, how you can make a plan of either direct cascading or routing it and then merging with the stream. One advantage with cascade drain is that it takes off the energy as the water flows down in every step of it. So it's a good energy dissipation arrangement as well. So when it comes to the bottom, it doesn't have much energy to erode the toe. So cascades are very effective, and added to that, if you have a gabion or any rough surface cascades, they also have very high Manning's coefficient and also dissipate the energy. Next, please. Subsurface drainage through pipe drains, and these are perforated pipe wrapped with geotextile. So that gives a very good arrangement, and you can penetrate these pipes very deep into the matrix, soil matrix as well. I sometimes recommend that even the weep hose which we create must have at least a short pipe, perforated pipe, and geotextile wrap with it if we are not giving any gravel layers or drainage details at the back of the retaining structures as well. Next, please. Now, I'll just show even from technical or calculation point of view that how this effect of lowering water, we know the qualitative nature of it, that it does affect. I'm now showing a quantitative nature of it. So if you see the left-hand side structure and right-hand side, so both are actually same cut slope. If you see the model, the top line is actually representing a slope and a cut and a water level. Only on the right hand side, if you see that we have made some arrangement of drain pipes, and that's where you'll see the next line, the second line, it's slightly below because we are trying to drain it off, and it only created probably 1 to 2 meter drop from the top surface. The phreatic line would drop just a meter or two below the top surface. So earlier, which was a saturated right up to the top phreatic line, with the drainage arrangement, we tried to lower it down by a meter or two. So that's the only difference between left-hand side sketch and right-hand side sketch. And with this, when we run the analysis, next slide, please. So when we run the analysis, you can see the factor of safety for left-hand side was 0.907. No change, the same C5 gamma, the soil properties, everything remaining same, just the water table lowering down. Right hand side, you can see the factor of safety is 1.338. Right, so this is the importance of drainage. If you can plan an effective drain, that will solve most of our problem. Next, please. Now, retaining structure, yes, sometimes we have to deal with retaining the earth as well. And there are various types of structures which can be created, whether it's a gravity retaining walls, crib or block walls, Gabion walls, even piles can be used as a retaining structure. And then RCC, reinforced earth, there are various types of buttress, gravity walls, you can name them. Next slide, please. I can show some pictures or details of it. So the crib walls, the gravity wall, the Gabion wall, the cantilever wall, or buttress wall, reinforced soil wall, all types of solutions are there. Next, please. Then even RCC wall, and you can give different shape depending on the site requirement and whether the key is required or not required for sliding. And as I said, piles can be used as a retaining structure too. Then the shape will get governed by the site conditions as well. There are also sheet pile walls, diaphragm walls, and so on. Next, just a glimpse of all these kind of structures. So crib wall, Gabion wall, and if you have noticed, there is a drum diaphragm wall, very innovative use. It was done in Kalyasur landslide. I think Dr. Bhandari was involved. So just the waste drums, from the bitumen, drums, you fill the sand, connect it through a cable rope or something, and then quickly erect as a quick mitigation measure initially. This may not be long term, but it can be very useful for certain situations. So various kinds of rock, walls can be constructed. Next. Now coming to the fourth intervention, which is internal reinforcement. So we can use the rock poles, micropiles, soil nailings, anchors. We can even grout the soil. So that's also internally reinforcing or adding strength to the ground. Then other treatment, heat treatment, electroosmotic, vegetation planting, vegetation roots can also act as a reinforcement to the soil. Right? So next, please. And various ways to plan it. So anchored pile walls or anchored walls. Some are, tie-back anchors. Some are friction-based anchor. So various types of anchors can be used. Next, please. Anchors, those are grouted and or otherwise nailing principles. So friction-based principles can also be used. And then you cover up the surfaces with cladding or shotcreting or anything. Next, please. Now coming to the fifth solution, which is surface protection. Since we have stabilized the slope, we also need stabilization of surface. The best method still can be vegetation, and that helps in erosion control as well as reinforcing the soil. So it can be done plain, some purists believe that just plain vegetation can also help in slope stabilization. To some extent, that's true. But since we cut very steep, we may need some structural intervention along with vegetation. So vegetated crib wall or vegetated gabions can also be practiced, and various other ways. 3D geonet can be used to retain. One issue we do face in certain arid areas, like maintaining the vegetation, is a problem sometimes. So we need to take care of all these practical aspects as well. Next, please. So some special methods people are using, and presently with NHI projects also, the cut and cover tunnel. So where the depth of tunnel cannot be too deep, we all know 2D to 3D overburden is required to make the tunnel. But such overburden is not there. In that case, also a tunnel can be constructed like cutting off the entire thing, building the shell of the tunnel, and then refill it back. so that you don't have to permanently acquire the top land if it can be filled back and used. One practical issue I have seen in a lot of project side, that this cut and cover works best when your left hand side, right hand side, both side hills are there, right? Somewhere people have used it, one side hill is there, the other side is actually a valley, and still went with cut and cover. It gets a lot of lateral pressure from one side. It can be designed, but I would suggest that the best location when you have to cut through the hill, uh, and both side there is confining pressure from either side. Next, please. I'll request the presenter that these slides one by one will take up. I'm just trying to now narrate one practical situation. So we have this condition, say, where we are cutting a hill to make some structure. This is the present slide shows just the normal ground, top vegetation, soil metrics, and a phreatic line. The blue colored line is a phreatic line. Very simplistic assumption. You can see from right hand side delta H, right? That's the height of phreatic line at the right hand side. On the left hand side, it comes down to a datum. And the length from right to left where the water is coming out is L1. The hydraulic gradient in the natural state, very simplistic assumption. I'm here not trying to go deep into the theory, but very simplistic. The inside gradient is delta H by L1 as written at the bottom. Next, please. Now, what we have is we want to construct a road. If you can see in the red line and substructure road or rail infrastructure and its formation level, this is our plan. Next, please. What do we do with this? So we want to cut the slope in a flat manner, but obviously we face a situation which is right of way is not available. Next slide, please. So we have to cut it very steep like this angle. Okay, we can still do it with some intervention like anchors or something. Next, please. So we plan our slope cut in benches, and this is our plan is ready, how we cut. Next, please. So we start cutting, and the best thing is that if you have planned this, then you also analyze and design rock anchors, its depth, strength, everything, and start putting as you cut. Because that's the easiest way when you are on the flat ground to put the nails rather than climbing back and then putting the nails. Then you start and keep cutting. Next slide, please. And keep switching to next one or two slides. So if you see, as you cut, the water is also altering its path, and it's also coming down. Next slide, please. So as you keep cutting, keep anchoring and going down, you will see that water profile or the phreatic line is also coming down because it can't go flat like that. Next, please. So now when you come down and your formation is ready, next, please. So now if you see the delta H remaining same, but the length has reduced. So at the toe of this cut slope, there will be huge exit gradient pressure, right? And this is where the problem starts, and which is where the requirement of a toe wall, right? Would like to highlight this, that toe wall is not a retaining structure, earth retaining structure. It is not actually taking care of the whole hill load. If the active pressure of hill comes, then the toe wall will be thrown away. But toe wall is necessary to keep this exit gradient in check. And that's the important part toe wall does, apart from giving some confinement at the toe, right? So this is one aspect everyone should keep in mind, that a toe wall is almost must in any hill cut slope, apart from maybe some rocky areas or something. Next, please. So coming to rockfall protection, it could be very small, fractured rock mass which is falling down, or a big blocky or large blocks which are falling down, or a huge massive blocks can also come down depending on how you have cut or what kind of layers or geological stratum is there. Some very fractured or highly weathered rock can come down like a soil slip surface as well. Next, please. So very simple diagnostic, and you can do some measures starting from just a warning measure that rock may come down to protection measure to passive measures, retention measure where you hold back the rock pieces onto the slope, or prevention measure and see that rockfall doesn't occur. So these are the measures mentioned in SR23 report also. Next, please. So in the rock also, you have to take care of any loose rock which is there and the failure is imminent. You better take it off, cut or trim or slope it. Next. Even in rock, very weak rocks or alternate layers of rock, then you may need some benching, and even that can be provided. But the cut slope could be very steep in these cases because of rock, but it may help. And particularly alternate layers, one sandstone, shales, or those kind of weak and strong layers are there. You must cut at the weaker rock top surface. That's so that the weak rock inside the matrix is safe. Next, please. There are always drapery systems or cortical strengthening where mesh with nails can be used. Next, please. And these all can be designed. SR23 gives a very good guideline on designing it as well. Then coming to superficial strengthening, shotcrete is very popular and known and common. But in cases of severely jointed rock formations, yes, it is good, or highly weathered surface or surfaces which are susceptible to very fast weathering. I would recommend that, but one caution with this kind of measure is that shotcreting actually blocks the water flow, and that's what we do not want to happen. So even if shotcrete is given, there is a way to give some drainage details where the water can still be taken out. Otherwise, most of the time, the way we propose, we do not want to block water passage. We want water to pass from every surface safely. That's the whole importance. Next, please. So reinforcing the slope face, similar to the shotcreting and graniting, is one way of it. And there are ways that you can actually put anchors first and then do the scaling also in order that the failure does not occur. So various practical measures can be adopted. Next, please. So when you are even anchoring, the detailing is important. The devil lies in the details, as they say. So what are we doing? Are we crossing the bedding planes properly so that the anchors are cutting the bedding planes and reinforcing them? The free length and fixed length concept. Sometimes when a shear zone is there within the layers of rock strata, then you may want to put sort of a cladding before the anchor is placed. You can put drainage pipe in rock surfaces also, because there are a lot of joints through which the seepage happens. And if the drainage pipe can intercept that and take it safely out, the material in between the joints do not flow out, the cementing material. So that's also important. Next, please. Sometimes for overhanging portion, either you cut it off or put a buttress to support it. Right. Next, please. When we talked about rolling down of rocks, right? So there could be flexible barriers, or you can put some embankments or rigid barriers as well. It all must be designed to the rolling mass energy stoppage energy required for that. Right? So even a soft embankment could absorb the energy. Similarly, flexible barriers are good to absorb the energy since they can deflect a lot. So they can actually absorb a lot of kinetic energy of moving rock. However, remember deflection is large, so don't place them very close to the road because otherwise the deflection would come right up to the road as well. Next, please. Then debris flow barrier. The difference between earlier rockfall barrier and debris flow is the difference in how the energy is. One is impact energy and one is like a slowly mobilized energy. So debris flow barriers are good for tributaries which are dumping a lot of debris into the main river. So you want to stop that and use that. So you can use debris flow barriers as well. Slight change in principles of working. Next, please. Then there are simple ditches which are very effective. So you don't need to do anything. Just make ditches on the side of the road, which can be designed actually in terms of width and height, so that any rockfall does not jump and comes onto the road surface. So those ditches can be planned. So left hand side, if you see that. Otherwise, again, on very steep slope where mitigation for continuous height is not possible, you may go for rock shades and with some dampening layer on the top. So any falling rock can jump from there and goes into the valley without disturbing the traffic. Tunnels are definitely options for this. Next, please. And these are some pictures of rock sheds and tunnels, like how it can be planned. A sloping base so that things go directly into valley. A lot of mountain stretch in Jammu and Kashmir may need this, and same probably for Uttarakhand and Himachal. Next, please. So when you think that we have dealt with all types of solution, let me tell you that it is very complex actually to analyze everything in a hill area. So I'm just listing out some very difficult material to deal with. Conglomerate material, soil and boulder mix. It's very difficult to deal this material because it neither behaves like a rock nor like a soil. So how to deal with it? Extremely varying geology. So while you are trying to give one solution, but vertically and horizontally, there could be varying geology and you may have to adopt multiple solutions within one cross section. Presence of treacherous soil, clay stones, right? So mudstones, shales, soluble rocks, which can later create a sinkhole or lead to chronic subsidence, phyllites, limestones, right? Huge subsurface flow, which can lead to piping and boiling, and again, the soil metrics fail underneath. It's an internal erosion. Alternating strata between weak and strong material, again, very difficult to deal with. Presence of underground aquifers, presence or absence of vegetation and plant in specific cases. So all these complex geological issues are there and it has to be attended case-to-case basis. Next, please. Now, while I have given types of solutions available, first, picking up the right solution, and second, quantifying the extent of solution required uh, is something where we have to delve deep into it and see how we approach the overall solutions. So here I'm trying to give an approach to evolve a solution. So the step-by-step or the scientific way to get to a solution is this: like, go have a reconnaissance survey, preliminary causes of problem you can identify at site, go do topographical survey and mapping, then plan a site investigation for geological mapping, so that you get rock strata details also, and geotechnical as well. So soil strength and their properties. For rock, what is the structural geology, data interpretation, stereo net plots, and for soil, usually lab investigation as well as field investigation through boreholes. Once you have all this data, when you have topography, when you have layers ready, you know which type of soil and rock is coming, their structural geology, then you are actually able to prepare a realistic slope model. You analyze that model, then you put your solution, analyze that slope, safe. You can in any case go ahead as it is. If it is unsafe, then you have solution options. Adopt an option, put it into the model, see whether we are safe. The factor of safety minimum recommended for seismic cases is 1 and for static 1.3, and whether we are attaining those. This has to be discussed and arrived at for each location, because every location there are some local issues, or you can take help of local say workers or practices. So we can localize the solution. We obviously are interested in giving detailed drawings so that it can be adopted at site, bill of quantity, specification, budgetary costing, and then go for execution. We finally recommend that instrumentation and monitoring, so that we know whatever we are putting up as a mitigation measure is working as planned or not, otherwise to be amended later on. Next, please. So I'll go step by step in all this process. Next, please. So here, first thing is observation, and when we go see this, we don't put enough probably emphasis in what we can notice. Like on the left hand side top photographs, you can see that water is visible only in 2 layers. So there could be a sandy seam through which the water is flowing. Similarly, if you go to the right top, there are alternative beds of shales, and they are vertical beds. They are not horizontal. And so how they will behave in one particular cross section. You can see surface weathering happening. And the last right bottom slide, if you notice, the water is coming through the joint of sandstone and shale. Shale being impermeable and sandstone permeable, that's where you expect the water. How you can use it in your designing, that you even plan your weep holes across this joint so that you can actually take maximum water out. So we see the practices of weep hole being specified 1.5 meters center to center. Actually, if you can plan and put it across these layers where from the water is coming, these will be very effective. Next, please. So then you can categorize what kind of strata is there: soil, rocky strata, mixed strata, what kind of erosion is happening, whether there is a streams nearby, there are waterfalls, or vegetation is present, absent, any piping, boiling phenomena happening around. Then slope are very high or low, flat or steep. So all this we actually note down. Next, please. Then you also notice actually construction feasibility, so how it can be done, whatever solution. So are there towers on the top? Is there a local habitat? Whether the access road is there to get and treat some particular layer on the top, and so on. Next, please. And we usually, our geologists, they carry these sheets, so we do not forget what is there. So this is actually taken from ground. So pardon for the poor handwriting, but this is what actually gets into the field. You go there, you notice, you make scribble and make notes, whatever there at site. And this actually is very helpful tool later on. Next, please. Now, topographic survey can be done with, nowadays very good techniques are available. Satellite imagery is there, LiDAR is there, and even drone surveys can be done, which is more like a photogrammetric survey. and which later can be turned into a topographical details as well, including a 3D image. Next, please. So this is a LiDAR image, one particular location. This is Saptashringi site near Nashik in Maharashtra. So we had scanned this whole hill. So this is what LiDARs can. You get the XYZ data, which is later very helpful because then you can plot your cross section anywhere you want. Next, please. This is a drone data, so bird's eye view. And very important, I particularly like drone survey because imagine standing right there on the ground. And if, I think my mouse will not be visible, but if I'm somewhere center there and looking up the hill, you can see a small slide which has happened. That was what I was seeing until I got this bird's eye view. And then I can see that the cracks are much beyond that slope which has been cut. So you can see very deep seated, that the crack lines are visible on the top and on the side. So it was very deep intervention eventually required for this site. So the drone gives very good idea on this. Next, please. In the drone, we can also zoom in and see even the texture of the soil and what kind of solution requirement. We can even measure the distances, everything. So once 3D is ready, it also reduces your repeated journey. Sometimes we get doubts, have I seen enough at the site or not? Now 3D is available in your table. Yes, sorry. So then it can be converted into a topographic map with contours. Next, please. And even marking the drainage layers. We also have geological mapping done. So we can actually categorize which type of soil, rock, layers, bedding, and everything into summarized into one map, geological map. So we know how to deal with a particular slope with such complexity. Next, please. We use geophysical method as well. ERT, electrical resistivity tomography, is usually used for detection of water. It also detects the layer strength, but I would primarily use it for detection of water. Next, please. So depending on resistivity, you can actually get some low resistivity or high resistivity pocket, and you can actually identify some water zones. You always get a confirmatory borehole done. Next, please. Now, the other geophysical method is seismic refraction tomography, SRT. So here we can get the layers of substratum by using seismic waves and intercepting them and seeing the speed of it. Next, please. So you can plot the layers and see what kind of layers underneath are, and where are you getting hard surfaces as well, depending on the velocity. Next, please. Yeah, so you can always then cross check. I would again caution that geophysical are qualitative methods. But it will give very good idea whether the substrata is uniform or disturbed or something, and then you can actually pick and choose the point to do borehole surveys. But it's always good to do borehole surveys and then corroborate the results of either the borehole and SRT so that you know your layers pretty sure. So this is one view where we are showing that how a borehole was taken, and then it was more or less corroborated with the SRT profile. Next, please. A very quick case study I'll pick up. This is mile 9 in Sikkim MRTH project. I'm not sure whether it has seen the light of the day, But just quick, the road is going in the middle, and you see we laid 5 ERT lines and then tested. So this is a slope from left down to Ranikola on the right. Next, please. So with each line of ERT, we could detect some water flows. If you see the concentrated green or blue colored areas, that's where anticipated water is. Next, please. And then we could connect all the lines result and actually could see that the piping was happening and 4 distinct line we were able to plot, right? Next, please. The dotted lines are the where the water was coming from. And then we did confirmatory borehole, always, to find that, and then gave enough measure so that we can intercept the piping and block it and still take the water out later on. Anyway, so that was the use of the ERT. So in any case, coming down next slide on geotechnical investigation, which is imperative that you always corroborate. One thing again I would like to highlight, in cut slope, actually the whole hill slope is visible to you. So you can say much better than a borehole, but what is underneath you do not know. So you may want to test that underneath, right? But doing just at the edge of the cut slope has no meaning because you are getting much better data through visual inspection rather than boreholes. Then you also do laboratory testing. You also do some soaking test and see whether the rock layers which you have found is susceptible to fast weathering. Next, please. We do RMR analysis. We do RMR analysis, something similar to what you do for tunnel, but this is to get some basic RMR and then use this data to get an equivalent properties in Mohr-Coulomb's way, that is cohesion and friction angle, equivalent cohesion and friction angle. So through geological strength index. Next, please. So whether soil and rock, and then in terms of rock, you also see the bedding planes, the joints, and map it. And then you define your stratum, 1, 2, 3, 4, 5, the way you have observed in boreholes and through observation. Next, please. This is how then you can set up all the stratum, its description, its properties, and you can set your model. All right. Next. Particularly for rock slope, a stereo net plotting will help you in type of failure which you may anticipate. Stereo net, so if you see the green line is so there is a slope line and then the rest all are the joint lines, how compared to slope they are tilting and orienting. In fact, I can explain it in the next slide better. So this is what you plot so that you know type of failure, how it will happen in a rock situation. So the solid line is the slope and the dotted line is either bedding plane or joint plane. So if you see that if the slope and joint plane in the same direction, right, then you see a sliding failure. So picture A, if you see, it's a sliding failure. And the way it is done, I can't explain stereo net all into this, but basically on the outer periphery, if the line is there, that means a flat slope. And if the line is cutting through the center of the circle, that means it's a vertical slope. And rest all is in between 0 to 90-degree slopes. So that's how it is plotted. Now, if you see joints in the second B picture, they are and a different orientation. So now you know there will be a wedge failure, which will, and the orientation is same as the direction of slope is. Now, sometimes the bedding planes are on the reverse side than the slope plane. So these we say favorable situation, but there could be some toppling failure which may occur. adjacency. And if it is very fractured mass, multiple joints and everything is there, then you can see a global failure or something similar to soil failure, which can occur. Next, please. Now we prepare a design basis report where these all types of, depending on again site situation, but you need global stability checks, you need internal stability checks of systems you have provided. If it's a wall, then bearing capacity, sliding, overturning checks. If it is a rock falling situation, then rockfall simulations, analysis for rockfall system, nailing design, subgrade design, and so on. Right. Next, please. Now you prepare the model and you are ready to run it. We usually use slope or slide software for limit equilibrium method analysis, and we use RS2 or phase 2 software for finite element analysis. The added value FEM gives is, we can even check the deformations, and sometimes slopes is okay, but deformations are very high, then we have to take care of additional measures. Next, please. Now you run the analysis, you find out your factor of safeties, how the concentration of force is coming. In FEM analysis, you can see that also. And in LEM, you can see the critical circle, how it runs. Next, please. When you do rockfall analysis or simulation, on right hand side picture you can see. So any jump profiles also you can model. This will help you what kind of energy you are getting at what level and where to put your rockfall barriers. Right. Even if you're using an embankment kind of barrier or if you're using a flexible mesh barrier, either way, first you need to do a trajectory analysis to determine the height, the impact energy, the location, and finalize it. Next, please. Now we are adding the solutions into the models. So in the top model, you can see we have used anchors and again running the slip circle analysis to improve the factor of safeties to the safer factor of safeties. In bottom also, you can see we have done a different type of analysis. There is pile foundation, then RCC wall, and then some reinforced soil wall to design the slope. Next, yeah, next please. Once you are done with your design, then you have to go for drawing board, sketch it out, plot your all joints and how you are going to give the details into it, whether it's a protection wall, where should be the location, how will you treat which zone. Some are with anchors, some with walls, some with pitching. So all has to be detailed into the sketch. Next. And if it's a RCC wall or reinforced soil wall, then the details of it also. Drainage details, as probably I have emphasized enough that every time the drainage detail becomes important. Where to give, how much to give. When you're making a reinforced soil wall, then even a chimney drain can be used behind the geogrid layers. So that will intercept the ground flow and then you can take it out smoothly through a pipe to the nearest drain. Next, please. And we all are doing this so that we know what kind of cost we are arriving at. So the description of work, costing, the figure is not important. I'm just saying that quantity estimates and costing is an important part of it as well. Next, please. Now coming to instrumentation and monitoring, and here also I emphasize that I'll go back saying that when we are talking about solutions, we are always using a term called mitigation, because there is still a possibility considering the complexity of hill area, that the failure may still happen. What we are trying to do with all these analysis is to mitigate. That means risk reduction of any failure. Risk elimination is very difficult in hilly area. If you try to do risk elimination, 100% guaranteed slope kind of, I get these things thrown at us also, that whatever you do, it must be guaranteed. In hill area, if you are giving a solution, a guaranteed solution may cost you, say, 1,000 crore, whereas a 90% solution can cost you maybe 100 crores only, right? So guaranteed solution is a term which should not be used. We should use a financially viable solution, technically and financially both viable solutions, then it makes sense. Now, why I'm giving this preamble is that which is why we can always doubt whether the solutions given are performing as estimated or not, and that's where the monitoring comes in place. That you monitor through pore water pressure, check pore water pressure, because water is one of the cause. Any sliding movements to be detected through sensors, right? Even the rain gauges can help you, because some of the early warning system can be linked straight away to how much rainfall is occurring. So the threshold could be 100 mm per hour for one location, it could be 120 mm per hour for another location. But once we have instruments, at least we can get some warning. Next, please. Even these things should be planned. The instrumentation can be planned. How to give it? I'm just showing one picture. This is from Nepal. We had worked. Location is probably Ramche in northern part of Nepal. So where to put which kind of instrument so that we get the data we want. For rock outcrops, we can put some prisms and do geodetic monitoring, that is through total station sighting or something. Automated total stations are also there. Then we can install piezometer, usually piezometer, inclinometer, and we put in proximity to each other so that we can relate pore water pressure to any settlements directly. And then settlement gauges at the top, rain gauges. So we can give a complete plan where we want to do it on a slope surface. Next, please. Yeah, later on, these all nowadays through IoTs, we can live monitor these systems. And this is thanks to IIT Mandi. They have put up a website also where they are monitoring, they are putting their instruments and monitoring. And this is a live system where even temperature, pressure, humidity, rainfall, everything is getting monitored, and location is also identified. Various location can be synced into one website. Now, how to use an alert alarm action plan, AAA plan, what we call alert alarm action. I'm giving very simple, simplistic, small module for it. In the bottom picture, if you see, so we are continuously monitoring the x-axis is timeline, the y-axis is pore pressure. Say the blue line is reading the current observation at site, right? When we do the slide designing, we know the factor of safety if the water rises. Say present water condition, my factor of safety is 1.5. If the water starts rising, the phreatic line starts rising in the hilly terrain, then my factor of safety would dip. Just single parameter alone is sufficient to dip my factor of safety. So say at about some level, factor of safety becomes 1.3. I have marked it in that red color if you can read. This all I'm talking about bottom figure. Then if you further rise it, it can come to very close 1.05, or when the failure is at factor of safety 1. So how will I do it? That I'm monitoring the situation. As the water level starts rising, the moment it touches my alert threshold, which is factor of safety of 1.3, I should get an alert SMS. Now, advantage of alert SMS is we still have time to do mitigation measure. We should rush to the site and find out where the water is coming, how to drain it off, and so on. However, if it is further rising and touching, going very close to one where the failure is there, then the alarm. The alarm system means just leave everything and rush out from the area where it is getting dangerous now. So such kind of alert alarm system can be placed, and live monitoring or live SMS can be obtained from the site. Next, please. So, yeah. Now, one important aspect is it's not that once the mitigation measures are done, you are maintenance free for life of the road. We all know that it's not possible. The rain and other things will keep on coming. There will be problems. So what kind of maintenance system we should adopt so that we stay away from any consequential hazard? Cleaning, very simple, cleaning of drains, smoothing of rain cuts and gullies, vegetating them if possible, patching out draperies. Sometimes the rock has fallen out, the draperies are open, you close them. Greening eroded areas, clearing of debris accumulated behind the draperies, cleaning and epoxy coating rusted elements. Anchors are rusting or loosening out or something. So there are, I can't give enough, but there could be a proper maintenance schedule which can be drawn and practiced, because this then becomes essence for longevity of the road. So next, please. I'll just show some case study photographs, and you can see the details that anchors are put first, and then the gabion front was later on erected, and eventually through an H frame it was connected to the anchors. So H frame connected gabion cladding wall. This is a project we did for Promont in Bangalore. We were consultant. Then drapery or high strength panel anchoring, you can see some work in progress, and greening the slope along with drapery can also be done. Next. Some of the outcomes of flattening the slope, and sometimes put the portals, make extra portal or false portal come out of the area, so that immediate next to the portal the landslide hazards are there. So if you come out and then cover them back, you will be safe. Next, please. So here also, where the tunnel portal is there, we proposed extension of tunnel. If you see within one picture, we tried to do a lot of things, take out the overburden, put a barrier system at the top of the tunnel, drapery system on the left hand side, right, and so on. So each location actually needs a lot of attention and detailing. Next, please. This is for Northeast Frontier Railway actually in Mizoram. And the solution, how it looks from top, so a barrier on top of the portal. Next, please. This was very challenging project we did in Bhutan. So this is Gyelephu Trongsa Highway. The location is called Box Cut. And from top to bottom, if you see, the erosion is happening. And just to give the idea of the measurements of it, from top to bottom or top to road itself is around 150 meter high, 150 to 200 meter. And below the road also, it goes down further 200 to 300 meter down. And this blocks this highway every year, and very challenging project. Here I also would like to point out one important aspect for those working in hills. There is always a tendency, the moment slide happens, we turn the road towards the hill and take a detour like that, and so we, as the hill cut is going deeper and deeper, we keep on turning the road towards the hill, hoping that a stable or rocky strata would come. But actually, we are going steeper and steeper in that way, and more susceptible to fall also. Again, location to location, the decision may differ, but in generic way, I would avoid that and see the protection work first rather than bending the road and circling around. Next, please. So what we came up for this solution, this is again a 3D view of how the solution can be implemented. So first, if you see, we tried to come out straight across it, but we still filled everything till the hill slope. And this is a reinforced soil wall structure we proposed. And if you can see the orientation, and this is all accommodating the topography of the area. We made a benched cut and vegetation on the right hand sides, greening. We lined all the drainage path, and drainage was one of the proposal is to take drainage down through a shaft, and later on the bottom, if you can see, it is coming out the culvert and going down again in a stepped way. So this is just a 3D overall image that how such big issues can also be tackled with careful planning. Next, please. There are various case studies, but I'm just showing some important, and that's all. So, in summary and conclusion, anticipation of issues related to slope stabilization is important, and then only you see the problems. Field survey, observations, investigations are necessary. Although you know the solutions, sometimes you believe just put a wall, put an anchor, put drainage. We know, but the extent of it, how much to put, how deep the anchor should go, what should be the spacing, what should be the diameter, what should be the strength of it, will still come out only through analysis, design, and knowing our field details. Right selection of solution. I can again go on ranting for a few things, but again, glimpse of it. Uh, Even a wall is selected, there is a choice. If you have a soil slope, cut slope or something, you can choose a more flexible structure. If you have a rock cut where you want to make a toe wall, maybe you want to go with PCC or concrete or gravity. So rigid to rigid, flexible to flexible, even those kind of finer details do matter. Right execution of it. A good solution with poor execution is of no use, right? And as always, I always mention that monitoring is still necessary, and maintenance for long-term survival is necessary. Next, please. So that's all from my side. You can always connect me to ashish@genstu.in. I have also given my phone number on the very front first slide, and we can interact more. It's a very, very elaborate, large subject. This is just a part or glimpse of it. I tried to cover as much as I could. Thank you.